Right, and welcome back to now the second class in environmental geography. Today we'll talk about specifically Earth systems. So today you will learn the origin, structure, and character of the four Earth systems, the nature of the geologic timescale and the major periods of Earth's history, methods for determining the age of Earth materials, and the rates of select Earth systems processes. So just to give you a quick refresher of what we talked about last time, and we talked about the so-called spheres, the four major systems, the atmosphere, which is basically the air, the hydrosphere, which includes water systems, both surface and groundwater, the geosphere, which is geologic, and the biosphere, all living material. Earth's interactive systems, they interact much like the body has its own systems. We have the nervous system, digestive system, and they work together. The systems transfer energy between themselves. And then the question is it an open or a closed system? The Earth's four systems. The Earth itself is a closed system, but the four systems are open, right? We learned that from last week. This is all a review. The origin of the geosphere. So now we're going to go through the geospheres one at a time. The geosphere started, it was just the birth of our planet, really. An immense cloud of gas and interstellar debris created from the Big Bang, and it was called a nebula. What is it? Well, the geosphere is the Earth with its deep molten portions. We'll go over those. Is it static or non-moving? That's a question. It is not static. It is not non-moving. It's dynamic. Although it goes very slowly, our geosphere is dynamic, and it has constant transfer of energy, but also matter. It builds mountains, it creates ocean basins, volcanoes, earthquakes. So it's a quite active sphere, maybe not as fast as the other ones. Sometimes you can't see it move, except for volcanoes sometimes, but it's still very active. And it is also provides all the minerals and energy resources that we want, except for, of course, solar and sun. But of the non-renewable resources, that's where most of our energy comes from. So about 4.5 billion years ago, before present, an immense cloud of gas and interstellar debris, which is called nebula, began to collapse under its own gravity. A very short explanation of gravity. I think we all know gravity when we see it, but how do you define gravity? It's very briefly the attractive force between two objects which have a mass. And of course the Earth has a very large mass, so if you were to drop something on, out of your hand, it's extremely attracted to the Earth, more than the Earth is attracted to the object you're dropping. So that's why we see it as gravity falling, but it's actually the attractive force between two objects. So there is a gravity. I mean, the Earth technically also falls up towards your object that you dropped, but not very much. It's not detectable, certainly. Okay, so most stars, like our sun, I'm assuming you all know that our sun is a star. They were born as clouds of gas called nebulae. The solar system was formed along with the sun, with the nebular cloud, and they became dense enough to collapse. And here you see in this picture, here the nebula, the forming of our solar system. Within the center our star called Sol. That's why it's called the solar system. A little bit more. So the denser and hotter center became the sun. The dust, rocks, and gases swirling around the sun coalesced to form the solar system. So there are rocky planets. They are Mercury, Venus, Earth, and Mars. So they're the first 4 planets. They're rocky planets. And then you have the large gaseous planets, Jupiter, Saturn, Uranus, and Neptune. And like I told you before, the reason why on the inside the first 4 planets are the rocky planets and the outer planets are the gas planets, because the the dust particles, the solid matter, is heavier, and so it swirled closer towards the largest mass, which is the sun. And the material that was less dense, had less mass, gases, were not as attracted to the center, the sun, as the solid material. So the further planets are gas, and the closest planets, Mercury, Venus, Earth, and Mars, are rocky. I'm not sure everybody knew that, but now you do, I guess. Here we go. So here are the 4 smallest planets, the rocky planets, and then you have quite a distance. And then you have the large, in descending order, the large gaseous planets. And these distances are not to scale, obviously. If they were, Earth would be 11 meters from the sun, and Neptune would be 330 meters from the sun. So this is obviously not drawn to scale. And the sun would be much, much bigger than it is now, that is here. That's the birth of our geosphere. Now let's go zooming in to the Earth itself. The Earth is, again, just like all of them and all the planets, an aggregation of nebular debris caused from many collisions of various sized particles over billions of years before we got a planet. The heat that was generated by the debris collisions were compressed through gravity, and it's compacted through decay of radioactive elements such as uranium and other radioactive elements. Also similar, I'm not sure if this is on this slide. We might get to it on later, but similar to the other planets, the heaviest elements form the center of the Earth. But at the beginning, the Earth was everywhere about the same. It was very homogeneous, and it took a while before the Earth divided into the different layers. The Moon, the people are not 100% sure. The current theory is that the Moon was formed after the early Earth, so half the size of present-day Earth. It was impacted by a meteor or another small planet, and part of the Earth was ejected into the space, and this mass of Earth that flung into space formed the Moon. And if you are a fan of, I forget I think it's called QI, a TV show on the BBC, they always ask how many moons does the Earth have, and it turns out that there are actually a lot of moons. We have one very large moon, but we have actually many smaller moons that were ejected at the same time from our planet. But they're very small. They're the size like cars. So the Earth's early surface would have been like a moonscape, right? So if you look at the moon, this is a picture of the moon. That would have been what our Earth looked like when it started to cool down. Because certainly at the very beginning of the formation of our planet, there were a lot of the planets were not completely formed, and so a lot of very large meteors were crashing into the Earth, and the impact of these formed craters onto our planet, and it would have looked like the Moon. The Moon does not have an active geosphere like we do. It doesn't have a crust that is constantly changing, and so it's held this snapshot. And now there are, of course, much fewer impacts on the moon, but these are all very old impacts. But we can see it on our planet. I've been here in Arizona. It's called the Great Crater. I have a mug at home somewhere. It's rare today to find these kind of impact craters. And well, the question is why. I actually already told you that. I already told you it. Um, First of all, we have an atmosphere which protects us. So most extraterrestrial objects, like meteors and comets, they burn up from friction as they pass through the atmosphere. So there are a lot of very small molecules in our atmosphere, and they grate it down as the falling object goes through the atmosphere. It gets grated down very quickly, and it's also very hot. Pass through the atmosphere, and the craters formed by those do not reach the surface. Are soon eroded by natural processes such as erosion. So varies. If something were to make it through the atmosphere, it'd normally be very small and form very small craters that would be eroded away quite quickly. This crater is 1.2 kilometers wide, and there's a small building. I think it's here. You can see the road, and then you can go into the building. It was formed. It's about 20 meters. Sorry, the crater is 1.2 meters, but the asteroid that struck in the center, the impact of the crater, was only 20 meters in diameter. This happened about 50,000 years ago, which is for a human very long time, but for our planet is a very short time. 50,000 years is not very long ago. And eventually, this is in the middle of a desert. It's not near any kind of fault line, so this will have to just erode naturally over the next, I don't know, a million years. It'll be gone, which is just a blink of the eye for our planet. Okay, now how is our planet then divided up? As the planet cooled off and it's not like I said, it's static, so it still kept swirling. The outside kind of cooled down, but the inside, it took a while for it to differentiate itself, but eventually it did. It began to differentiate itself into different layers. Like I mentioned actually already, the denser elements such as iron and nickel, they migrated to the center of our planet. They are very deep, and the molten core of the planet is almost 100% iron and nickel. Less dense elements like silicon, aluminum, oxygen, potassium, and sodium, they floated, well, yeah, floated because it was still a liquid. They floated to the surface, and because of this, the elements have three different layers called the core, which is obviously it's the center of the planet. It's the core. The mantle is this part, and the crust, which we walk around on today. All right. So as again, to quickly reiterate, to restate it, the internal structure of our Earth is differentiated by composition, and this includes an inner and outer core, a thick mantle, and a very thin crust. But we'll get to that. The crust under the continents is thicker and less dense than crust under the oceans. Yeah, so it forms not only the land that we walk on, but also it's under the oceans, which is thinner and less dense. The core has two parts, a solid inner core, which is about 1,200 kilometers thick. That is approximately 1.7% of the Earth's total mass, and so it's almost solid iron and nickel. The liquid outer core is about 2,250 kilometers. It represents 30.8% of Earth's mass, and it's composed also of iron and nickel, but then 10% of lighter elements, perhaps, and again we're saying perhaps because we've never really been there. We've never drilled that far of oxygen and sulfur. And composition of the core is inferred. We can't drill to the core; it's much too far. The composition there are science fantasy movies where people go through the core of the planet to the other side. That's very fascinating, but I'll have Elon Musk get on that. That'll be his next project. So the composition of the core inferred from studies focusing on density, the composition of the iron-rich meteorites that are thought to be pieces of other planetary cores, and the manner in which seismic waves, which are also called earthquakes, how they pass or don't pass through it. So we know how earthquake waves, seismic waves pass, and we can measure the density and therefore the composition of material. Even if we've never been there, we can infer it. So it hasn't been directly measured, but inferred from measurements. Below the crust, the majority of Earth's interior is the mantle. Like I said before, it's 2850 kilometers thick. Why does it say 67%? Before it says 30%. That's not right. I think it's 67%. That should be, this should say, my excuse, I don't, oh, that's the outer core. I've got myself confused. Hopefully I spoke correctly, and now I've probably confused you by something that you shouldn't be confused about. This is the inner core and the outer core, and now this is the mantle. Okay. Right, so the mantle, moving along, nothing to see here. The mantle is 67% of the Earth's total mass. The composition is a little bit variable. It includes, mostly magnesium, and decreasing abundance of, as you go down, decreasing abundance of silicon and oxygen, and very little iron. Compositional knowledge draws on studies on Earth's density from meteorites, seismic waves, and more information about upper mantle that's been brought from Earth's surface. So volcanoes are directly connected to the mantle. If you didn't know, well, I guess you could. I told you that the mantle is liquid, right? So it wouldn't be surprising then that volcanoes, which produce several things, we might go over that, but in what we see as lava or magma underground is liquid, so it's directly connected to the mantle. And then the crust, the thinnest layer, it's the outer skin of the Earth, approximately 80 kilometers thick at its deepest point. It contains rocks that can be examined on the Earth's surface. There are two different types of crust. The continental crust, which is about 30 to 40 kilometers thick, and it's mostly granite. That's where we walk around on. And then you have oceanic crust, that's 5 to 8 kilometers, and that's under the ocean. It's much less thick, and the rock that you find at the bottom of the ocean is basalt. Okay, so here's a table to show you the difference. The oceanic crust, 5 to 8 kilometers, the oldest about 180 million years old, and basalt is the dominant rock type. Continental is thicker, it's 30 to 40 kilometers, it's much thicker. It's older, renews itself less. It's about 4 billion is the oldest, and its dominant rock type is granite. I think that's a question on the quiz. I'm just heads up there. Defining Earth's interior. Now we have a cross section, maybe to make it a little bit easier to see. So we know about these different boundaries because of seismic waves and the velocity that they travel through different regions of the core, mantle, and crust. So we have the three. We have core, mantle, crust. The core has an inner and an outer, but the mantle and the crust are actually also divided. So these include the inner core, outer core, the lower mantle, the mantle transition zone, the upper mantle, which you see here, right? So inner core, outer core, lower mantle, upper mantle, and then you have the asthenosphere and the lithosphere here, and at the very top, the crust. There are physically differences between the inner core. Wait, yeah. They the inner core is solid, as I mentioned. The outer core is liquid. The very dense inner core, in spite of extreme high temperatures, because of the very high pressures. If you think about the chemistry, um, such high pressures that it's solid. The outer core is liquid because the pressures are slightly lower, but the temperatures are still high, and they exceed the melting point of iron. We know that it is liquid because it slows down a very fast seismic wave, and other seismic waves cannot pass through it. The lower mantle and mantle transition, so now we've divided the mantle up, is solid rock in the lower mantle, and that occurs from 2,900 kilometers to 660 kilometers in depth. It gradually decreases in density downward toward the boundary and to the molten outer core. So it becomes more dense as you go up, becomes other way around. It increases in density as you go down, and it decreases as you come up. Although the upper and lower mantle rocks are similar in composition, the higher phosphorus in the lower mantle makes minerals. They're different than in the upper crust. There is a transition zone between 660 kilometers and 410 kilometers. The upper mantle and the moho, the upper mantle lies above the transition zone and extends towards the base of the crust, is defined by an abrupt increase in seismic wave velocities, and the moho is, I don't know how to say this name, Mohorovicic, who discovered this. The brittle uppermost mantle and crust is called the lithosphere, and this is very important to understand the lithosphere because of we'll be talking about tectonic plates. The lithosphere is where these are located. A weak zone of upper mantle just below the lithosphere is the asthenosphere. So the asthenosphere is underneath the plates, which are moving, and it's liquid. The asthenosphere and lithosphere also differentiate because of seismic velocities. Let's take a quick break because I've been talking now for at least 15 minutes about the planet, about the geosphere. Before I move on to the atmosphere, were there any questions that you wanted to ask? I guess I have questions to ask. I'll to quiz you. So, who can tell me what was the large cloud of dust and gas at the beginning of formation of our solar system? What was that called? Ah, ruins fast. That was easy. Let me think of a more difficult question. Name the 4 rocky planets. A little bit longer. I think that the Earth's a gimme. You should know that. Anybody know? What are the 4 rocky planets? Ah, come on, guys, give it a go. There you go. Ha ha ha. Very funny, Clara. So Mercury, Venus, Earth, and Mars. No, Venus is one. And what are the gassy planets then? There you go. Thank you, Jerry. I think he was paused and ready for that one. He knew it was coming. Let's see. Our planet was formed how long ago, approximately? Yes, you got it, Fernando. Um, hmm. What are the the three major ones are the core, the mantle, and the crust. What the crust is made of two different types of crust, and don't say thin crust and deep dish. But what are the two different types of crust? Correct, Julie. And which one's thicker? You guys are so smart. There you go. Okay. And let's see. Ooh, here's one. What two elements form almost 100% of the core? Iron and nickel. Oh, our students are so smart. Okay, good. We refreshed it slightly, so I'll go on to the atmosphere, and after atmosphere, I'll take a 10-minute break because I also, even though I say, I have a voice of an angel, it's true. Uh, but even I can sometimes zone out listening to myself for too long. So we'll do another 10 minutes, 15 minutes. We'll go through the atmosphere and then take a short break. So the atmosphere. The atmosphere includes the gases that surround the geosphere. So we call this air, and it comprises the atmosphere. The atmosphere extends from the Earth's surface upward for many hundreds of kilometers. So there's no real distinct top. It just gradually becomes less dense and merges with empty space. It should be between quotes, empty space, because of course space is also not empty completely. It's just a lot of space in between the molecules, which is why we call it space. That there's space between the molecules around us too. So anyway, it also includes gases that fill voids in near surface geosphere, so also known as caves and caverns. The atmosphere is Earth's most dynamic system and is the vessel for life-dependent gases, at least our lives, such as and those of plants, such as oxygen and carbon dioxide. There are organisms that do not need oxygen or carbon dioxide, of course, but I would say that the dominance of the biosphere is on one of those two gases. Origin of the atmosphere. The first atmosphere looked nothing like the atmosphere we have today. Gases were part of the nebular cloud, as I mentioned, that form our solar system. The gases that were very common in the nebular clouds, and still today in the outer gaseous planets, they included hydrogen, helium, methane or methane, as you like to pronounce it, and ammonia. The Earth's first atmosphere probably included such gases. Unlike the geosphere, where there's no way to measure or infer from different measurements. Here we are using uh, deductive reasoning that our first atmosphere probably had these gases. Although, yeah, sometimes you can get very old um, cores and get the gases right in between, but this is billions of years ago. I'm not sure how easy it is to get a rock from 4 billion years ago to analyze the gases in between the silica. So prior to the Earth's complete differentiation of the geosphere, while it was still very hot, and perhaps before a liquid outer core was fully developed, and before the complete aggregation, gravity could not hold these gases close to the Earth. So the first atmosphere, um, we infer it just left really. The second atmosphere had more volatiles, which are easily vaporized elements or compounds. The volatiles were present in nebular material that formed the initial solid Earth. These included hydrogen, carbon, and nitrogen. These are very common elements in our atmosphere today as well. And as well as compounds formed from these elements such as water, carbon dioxide, and ammonia. Certainly water and carbon dioxide are very common in our air. These elements and compounds are characteristics of primitive meteorites called carbonaceous chondrites, thought to be representative of the nebular cloud composition that condensed to form the solar system. So the first atmosphere we can't really measure too well. The second atmosphere we are now measuring um, meteorites and saying, oh, this is probably what the Earth was like before. And thus materials in the Earth, the early solid Earth that contained volatile components, if vaporized, could have contributed to the formation of the Earth's atmosphere. So as these carbonaceous chondrites plunged into our planet, they would have released these gases. The outgassing, or the forming of the second atmosphere, we say a more stable atmosphere. So what dominant process was active during the first billion years of Earth's existence to form the second atmosphere? Well, we don't think there was life, so we're assuming that this would be outgassing. So outgassing is through volcanism, through volcanoes. Volatile components came from the interior, so the asthenosphere and maybe even deeper, uh, to the Earth's surface and atmosphere. This includes molten rock, which is magma, and when it hits the surface, that's called lava, and that releases a lot of gases. And so today we can measure the gases erupting from a volcano, and that's how we can directly measure what is coming from the asthenosphere. It's an estimate of what early volcanism released to the atmosphere, and we look at present-day volcanic eruptions, which release a lot of water vapor, carbon dioxide, nitrogen, and sulfurous compounds, especially sulfur dioxide, to the atmosphere. Has anybody here been to a volcano, an active volcano? Just one person? A show of hands ups. We have not thumbs up, but hands ups. I think that's, there we go. There we go. May I ask, where did you guys go? Or maybe you went to several volcanoes. I have to say, I travel quite a bit. I've seen several volcanoes. I love volcanoes. Ooh, I was just talking the other day that Iceland is like my top destination. Ooh, Italy. Where in Italy, Lynn? Sicily? Ah, is it near Sicily? Is it Stromboli? Yeah, yeah. I visited Stromboli. Ooh, let's see. Timanfaya, Lanzarote. I've never been to Lanzarote. I've been to well, actually, I have. I think I changed planes there, but La Palma. Yeah, the Canary Islands are extremely active. I could actually. We have a class on. I have a class on volcanoes. I love volcanoes. I've been to many, many volcanoes there. The stinkiest volcano I've ever been to was on in Indonesia. It had a lot of sulfur coming out, um, but most volcanoes are, I think, a lot of fun. Very exciting. Recommend it. So, Volcanism-Clues to outgassing from the Earth's second atmosphere. The atmosphere created by outgassing Earth's early history is through water vapor and carbon dioxide, as I said before, sulfur compounds, hydrogen, and then these reacted and created ammonia and methane. Carbon dioxide, methane, and water vapor are gases that cause an atmosphere's temperature to rise. These are all greenhouse gases. I mentioned in not yesterday, it was Friday's class, that the greenhouse effect is just a fact, and that we've had this greenhouse gases for a very long time, since the formation of our planet 4.5 billion years ago. And at this time, during the second atmosphere, the climate during the time it increased. So it was very, very warm. There were no polar ice caps, no liquid water. Um, there was very little or no, well, no. As a chemist, I don't like saying that there is no. There was undetectable amounts of oxygen in the atmosphere. And life as we know it did not exist for the first billion years of our planet. Now, the third atmosphere, we call it the third atmosphere, it's today's atmosphere, has this composition. About 78% nitrogen gas, N2, 21% O2, oxygen gas. Water vapor is between 0 to 4%, depending on where you are. You can feel it. Argon, which is a stable gas, which does not react. It's about 1%, a little bit less than 1%. Carbon dioxide, which is a variable because it is increasing every year. Neon, helium, methane is quite low. Hydrogen gas, nitrous oxide, and ozone become very small trace elements in our atmosphere. Although the composition of the atmosphere changes as you go further above the surface. So it's called the third atmosphere. That's the atmosphere we have today. And the table 2.1 is the one we just saw. Big changes were needed to transform the Earth's, as you see in the table. Look at this, oxygen. Suddenly, we went from basically no oxygen to having 21% oxygen. So there must have been something going on there. We'll get to that. Large volumes of H2O and CO2 have been removed, and a lot of nitrogen and oxygen were added into the atmosphere. So my question to you, how did this happen? How did we get oxygen on our planet? It wasn't from volcanoes. So it wasn't the geosphere, for example. Yeah, yeah. So bacteria, plants. So oxygen first formed on our planet because of the biosphere, and that will be talked about soon. So an excess of H2O went to the hydrosphere. So a lot of the water condensed as it cooled down, and by 3.5 billion years, billion years before present, Earth's oceans had formed from water that precipitated from the second atmosphere as the geosphere began to cool down. Once the oceans existed, CO2 from the atmosphere began to dissolve into the waters. As I mentioned yesterday, when water drops through the atmosphere, it takes on CO2, which is why rain has a slightly lower pH than 7, because it has CO2 in it. This then eventually goes into the oceans, where the CO2 has its has a sink. We call it a CO2 sink. Dissolved CO2 in turn reacts with calcium to form calcium carbonate, which starts to precipitate and accumulate on the seafloor. Here you can see calcium carbonate on the seafloor. And because many organisms incorporate calcium carbonate into their shells and skeletons, they also accumulate to the seafloor. The rate of precipitation increases once living plants and animals came upon the scene. So as first the rain caused the CO2 to go into the water, organisms used this the CO2 along with the calcium to form calcium carbonate, and now we have these. I believe this is Dover. This is the cliffs of Dover, which are very famous for their white color, and it's uh, pure calcium. No, almost pure calcium carbonate. And that, even though it's very beautiful, and if you go into the ocean, of course, this is a common occurrence. Okay, so most of the seafloor calcium carbonate accumulates gradually, turns into rocks, and become part of the geosphere. So that's a question. Some people ask, well, what's the difference between organic chemistry and non-organic chemistry? It's not just carbon, because calcium carbonate comes from plants, right? So seashells form a lot of rock. The geosphere is the world's largest carbon reservoir and a global sink for CO2. The concentration of CO2 in the atmosphere slowly decreased as it was transferred to the geosphere, which is why some people say, in the past we did not have polar ice caps. That's absolutely true, um, because the planet cooled down and the CO2, which was a greenhouse gas, was transferred to the geosphere. But recently we are increasing the CO2. It would be to use the words from the last class, a gaining system, because the reservoir is increasing. In the modern atmosphere, we have lots of nitrogen. It says nearly 80%, I believe at 78% nitrogen. And even though nitrogen increased during Earth's early history, there was still no free oxygen. And as I stated, and you guys also guessed, Amish said, the origin of the atmosphere's free oxygen is tied to changes in the biosphere, or I should say the birth of the biosphere. Oxygen comes from the biosphere, almost all of it. So some of the earliest life forms on Earth, as Amish said, is cyanobacteria. These are photosynthetic bacteria which use sunlight to convert CO2 and water into sugar that they use, their food, and oxygen. And this is called photosynthesis. I'm sure you've all heard of that before. Cyanobacteria started also called blue-green algae, but they are not algae, they are bacteria. They started making oxygen about 3.5 billion years before present, but it didn't really increase that much for another billion years. Why is that? So about 2 billion years ago, so 1.5 billion years after cyanobacteria, most of the material that was readily reacted to was used up. Slowly, oxygen began to increase as photosynthetic organisms increased. So as cyanobacteria slowly evolved into larger, more complex, and then eventually vascular plants, which then populated the land around us, came out of the oceans. So about 500 million years before present, the land plants appeared, and that's when the oxygen levels became what it is today. So the cyanobacteria kicked it off. These cyanobacteria gradually, slowly evolved into land plants and vascular plants, which really kicked off the oxygen that we have today. And because of this, there was a tremendous expansion of the diversity at this time. And we talk about some geologic time periods. This is called the Cambrian explosion, the Cambrian period explosion. You've probably heard about that before. So, stores of early produced oxygen. So what was the sink for early produced oxygen? And that is rocks. Newly formed oxygen from the cyanobacteria, reacted with the iron and the sulfur on the Earth's surface, and dissolved into the oceans. Water actually can hold quite a lot of oxygen. The chemicals reacted to form minerals, became iron oxides, which accumulated in sediments to become what is known as banded iron formation, BIFs. BIFs are sinks where Earth's early oxygen is stored today. So here you have a geologist going around measuring that. The structure of the atmosphere, here's the surface. We're going through this. It's about 480 kilometers thick, approximately. It has two layers defined by compositional variation, the homosphere and the heterosphere. Solar radiation interacts with the Earth's surface, and the atmosphere produces temperature variations into four atmospheric layers. And the four layers are the troposphere, the stratosphere, the mesosphere, and the thermosphere. So the troposphere is about 7 kilometers from the poles and near the equator, 17 kilometers near the equator. A change in the temperature in the troposphere is related to the heating of Earth's surface by solar radiation, so it cools. The surface is warmer than if you go up a few kilometers. The troposphere is the most dynamic within the atmosphere. It's where we live. It's where all our weather happens. About half of the mass of the total atmosphere is in the lower 5 kilometers of the troposphere, so it's much more dense. The stratosphere, the temperatures increase. You may not know this, but in the troposphere, the temperatures decrease as you go up, but in the stratosphere, it starts increasing again. Um, it has higher temps in the stratosphere versus though under in the troposphere, which prevents the rising and crossing of this zone. So this is called the tropopause. Between the troposphere and the stratosphere is the tropopause, and it's caused by the change in temperature. Just like if you've jumped into a lake, the top layer of a lake is very warm, and if your toes feel very cool, it's because of the temperature differences. And this is the same difference between the stratosphere and the troposphere. It's called by a tropopause. The top of the stratosphere is marked by a decrease, and this is called the stratopause, and that is about 50 kilometers from the Earth's surface. The stratosphere contains ozone, which is a protector of the biosphere. I'm not sure if you've learned this from chemistry classes before, but within the stratosphere there's a lot of there are oxygen molecules which absorb short wavelength ultraviolet radiation, which is the most damaging radiation from the sun, and that splits into single oxygen atoms, which bonds to the O2 molecules to form ozone. And then ozone again absorbs UV and breaks it down into O2. So it's a cycle where the O2 is broken down into single O, which forms O3, which then gets broken down into O2. It's formed slowly and reacts with sunlight. And if this ozone layer is not there, in the past it disappeared in southern and northern parts, you get much higher UV radiation, so it's very harmful for all life on our planet, both plants and animals. Some characteristics of the stratosphere: as you go upward, temperatures increase through the stratosphere. Small quantities of water vapor and stratified character of the stratosphere make it generally cloudless, so you're way above the clouds, and the winds are parallel to Earth's surface. So it's what we see as blue, really. The mesosphere is above that. Here the temperatures now decrease to a boundary zone called the mesopause, where the lowest temperatures in the atmosphere are present. Temperatures decrease upwards through the mesosphere, reflecting less concentration of gas molecules that absorb UV radiation. It's also related to the presence of small amounts of CO2, which absorb re-radiated solar energy. But there are a few other gases, so it's mostly just CO2. Here the concentration is very low, but there's still enough to have some effects. So there are friction from the few gas molecules. So you wouldn't want to have a satellite up in the mesosphere. It would have a lot of friction for a very long time. The exosphere is just beyond the mesosphere, and that was what we define as space. Outer atmospheric layers above the mesosphere increase, and the molecules decrease as you go through it. That's of altitudes up to 180 kilometers. Compositionally defined, the same as the heterosphere, the temperatures increase upward in the thermosphere due to interaction of intense solar radiation. So it's quite hot in space. People don't realize that. They think space can be cold, but you have direct solar radiation. The astronauts and cosmonauts, they have air conditioning in their spacesuits, not heaters. Although they do have heaters too when down the other side of the planet. The thermosphere, solar radiation is very intense. The change of gas molecules charged particles, ions, which cause what we call the aurora borealis in the north and the aurora australis in the south, also known as the northern lights in the north and the southern lights in the south. This is ions formed by the collision of solar particles in the gases. We will take a pause there because I think we've covered quite a bit. We are more than halfway, and I'm personally going to get a cup of coffee and I will see you back in 7 minutes. I'll start at 9:50 according to my clock. Now the hydrosphere. We have two more: the hydrosphere and the biosphere. Leaving the best for last because that's what we are. We're the biosphere. It's directly connected between the solar energy of the Earth's processes. It consists of all water in all oceans, on land, in streams and lakes, and glaciers, so liquid water, solid water, in our atmosphere underground, and our water planet, because we call the Earth a water planet because it's covered 71% of our surface is water. It is uniquely positioned in the solar system so that water can exist in all three phases: solid, liquid, and gas, which is also called water vapor. So how did we get so much water on our planet? It's part of the original nebular debris that coalesced, condensed to form the Earth. Other contributions were the volcanic outgassing, released volatiles including water vapor, into the Earth's second atmosphere. And upon the cooling, as we said before, this condensed and became liquid. Oldest known rocks that formed from ocean sediments about 3.8 billion years old, and they confirm that there are some compositional characteristics of the seventh atmosphere, that oceans were present, and therefore also a hydrosphere from 3.8 billion years ago. So the hydrosphere has been along, not as long as the geosphere, but quite a long time. So you might have seen this before in earlier classes. Unlike the atmospheric geosphere, the hydrosphere lacks any internal structure, but it possesses distinct reservoirs. So if we have all water on our planet, the world's oceans are 97.2%. Only 2.8% is fresh water, so not salt water. And of this fresh water, 68.6% is ice, 30.1% is underground, and only 1.3% is surface water. So all the rivers and lakes in the world only represent 1.3% of 2.8% of all the waters. So 1% of 3% approximately. So very, very little. That's 0.03% of all water is surface water. And not all of that water is drinkable or potable. Another word for drinkable is potable. The hydrosphere's reservoirs, so fresh water, 2.8 of Earth's surface water is fresh water, and these are distributed into lakes, streams, rivers, underground, and in the atmosphere, but small compared to Earth's fresh reservoir in the glaciers, ice caps, and ice sheets. 68.6% of Earth's fresh water is ice. The ocean contains 97.2% of all the water. A continuous body of water that covers 71% of Earth's surface and is in some areas 3 kilometers deep. Internal structure is defined by variations of salinity and temperature. So as I mentioned in lakes, the study of lakes is called limnology. So if you ever take a class in limnology, you'll see that the lake has different layers, but the oceans as well. About 200 meters thick in the upper layer of the ocean that is warmed by the sun and mixed by the waves and the currents and surface winds. The lower layer, as for depths below 1,000 meters, solar radiation has very little effect, and the water temperatures are very low. So between 0 and 4%, 0 and 4 degrees Celsius, and water can still be in motion because of salinity. Salty water is more dense, and therefore it remains liquid at 0 degrees Celsius. It sinks, obviously, and there has major influence on global climate because of specific heat compared to the atmosphere. Specific heat is an understanding of the amount of energy, and this is seen as heat, the amount of energy that molecules can absorb. Water is a very strong molecule, so therefore it can absorb a lot of energy. So water has a very high specific heat, which means it can absorb and retain warmth. Glaciers, if snow accumulates, these form glaciers. And this is, you can see there's a glacier in southern Alaska. Seasonal conditions enable glaciers to form at high elevations in mountains or high altitudes. Maybe some of you have been to some glaciers. Um, if you've gone skiing in the Alps, for example, you have glaciers. And they form small patches in some places, and other places very large rivers of ice that slowly flow down slope and carve ravines into mountains. Glaciers coalesce and become much larger, so these are called ice caps. They're up to 50,000 square kilometers, and ice sheets, which are greater than 50,000 square kilometers. In the modern world, the ice covers about 10% of the Earth's land area, mostly as ice sheets in Greenland or in Antarctica, but as most people know, these are degrading. The water cycle. The hydrosphere interacts with other Earth systems in the water cycle and transfer resources between them. So the atmosphere over the oceans is a key part of the water cycle. 86% of water vapor is obtained through evaporation from the seas. You see that here in the photo. 86% of its water vapor. When air rises, it then cools, causing water vapor to turn into tiny droplets, which we call clouds, where air temperature falls, and as when air rises along mountains, the liquid water droplets condense and fall to the Earth's surface, right? In precipitation, either as rain, snow, or ice, or hail to the land. So precipitation is in 3 reservoirs: the ice, the surface water, and don't forget the groundwater. I think there's more groundwater than there is surface water. Rivers and streams carry water back to the oceans and to coastal settings. Water is used by plants and absorbed by animals before it can go through respiration and transpiration, before it can get to the ocean in many parts. And this processes interact between the atmosphere, biosphere, and geosphere. Lastly, we have the biosphere. It consists of all life on the planet, both large and small, from a molecular level to very large, vast, complex ecosystems. It produces food, has a very large role in the carbon cycle. It's a pollution filter. It captures energy and aids in soil development. And so what started evolution to make life so diverse? So from chemical and fossil, so paleontological evidence, paleo meaning old, records, ancient rocks provide insights into life. So fossils from about 2 billion years ago and younger. Examples of fossils can be actual remains or imprints of an organism on its hard parts, shells, or dinosaur bones. So here's what I referred to, figure 2.18. Here you see the shell imprint. Here you see the fossilized bones this is a T-Rex, and also the impressions of plants. I believe a fern from 200 to 300 million years ago. So these are called ammonites, shelled animals. This form squid and octopi. Side note: the plural of octopus is mostly either octopuses or octopody. Anyway, so the plural of puss is podes, but it's slightly annoying when I see that. Octopi. Octopuses is also acceptable. Some of the oldest fossils. So bacteria from about 3.2 billion years ago have been found in sedimentary rocks in Australia. Stromatolites are fossils found in even older rocks. So as much as 3.5 billion, muddy sediments trapped mats of bacteria, and the descendants of stromatolite-forming bacteria still inhabit the coastal environments. It's the they have a hard chitinous outer layer. Cyanobacteria, the first photosynthetic organisms lived in stromatolites today, but it's unknown if bacteria lived in very old stromatolites were photosynthetic. We don't know that because there are a lot of bacteria that live without carbon dioxide and do not form oxygen. They live on like iron production in deep water vents in the ocean. So in the 17th century, there was a Danish anatomist, Nicholas Steno, who's also called Niels Stensen, recognized tongue stones from fossilized shark teeth, and he compared them to modern shark anatomy in the fossil record, and established that the fossil represented former life in the former seas because there were no shark teeth as big as the teeth of the shark, which we presently know. Early evolution of thoughts. So by the end of 18th century, fossils became the focus of naturalists. There was vertebrate fossils were the specialty of Georges Cuvier, and then invertebrate fossils were specialty of Jean-Baptiste Lamarck, and they were both members of the French Museum of Natural History. And they came up with their own ideas. We think of Darwin today, but this is pre-Darwinian theory. So in 1798, Cuvier showed that vertebrate fossils represent species that no longer exist. For example, that mammoths were different from elephants, and that mammoths were extinct. And this seems very obvious to us, but somebody had to make this observation, and then Lamarck recognized the complexity changed through time. So Cuvier demonstrated that mammoths were we see these fossils. They look like elephants, but they are not elephants. Later came Darwin and Wallace. Charles Darwin and Alfred Russel Wallace came in parallel around the same time on the idea of what we now call natural selection. Wallace, I believe, published his work slightly earlier, but Darwin was had not published yet, so we contribute to both people. Wallace was a biogeographer. He looked at distribution of species and came up with this idea of natural selection. They communicated to each other and shared specimens, and they jointly presented their ideas in 1858. Darwin and Wallace are very famous, especially Darwin. We call it a Darwinian evolution. Darwin published his book in 1859 on the origin of the species, and Wallace continued his studies. From this book, his best examples came from his time on an exploratory vessel called the HMS Beagle. On the HMS Beagle, he went down to South America and then through Asia on a trip around Africa and back. And mostly we know him from his work in the Galapagos Islands, which are here off of the west coast of South America, where there are tortoises to this day, I think, who still are alive that Darwin met. One of the studies that he did in the Galapagos Islands was a very famous one on birds, on finches, Darwin's finches. And he noticed that there were many different types of finches on this island, on the Galapagos Islands, actually plural. And each one was specifically selected for what it was eating. So the insect eaters had a certain type of beak specific to an insect that they were eating, either in a medium tree finch, or warbler finch. Cactus eaters, they had to get around the well, they didn't eat cactuses, but they ate insects in the cactuses. They had to get around the spikes of the cactus. Ground finches did not need to go as deep, but they need to burrow around. And then they had a finch which ate fruit. And each of these finches, their bodies were very similar, but their beaks were very different. And his idea with the 13 different species of finches he met, that their beaks adapted to slowly over time, through competition, to be able to get to one niche. See, was that it for Darwin? I guess we're done with Darwin. So from this idea of competition, which Darwin and Wallace came, of natural selection, we now have a more nuanced idea called punctuated equilibrium. So while yes, the uh, the birds did differentiate because of the different niches that they were eating, there were also times of great mass extinction throughout our history. So you see here, this is the number of families of animals through time, and there were several events that happened to uh, to kill off a lot of the animals. These mass extinctions. There were at least 5 in the last 540 million years, and most recently was about 65 million years before present. And these are the Ordovician, Devonian, Permo-Triassic, and the End-Triassic extinction, and the Cretaceous Tertiary extinction. There are several theories about the death of the dinosaurs, and certainly a very good one is here off of in the Gulf of Mexico, off of the Yucatan Peninsula. There is an impact site on which 65 million years ago a very large asteroid impacted our planet, which would have caused a lot of massive amounts of dust to cloud our atmosphere for many, many years. And then, of course, if there's no sun, there's very little food, very little plants. And this is an example of, although I've recently heard other theories about why the extinctions took place, but that's certainly, I think, the dominant one right now. Another extinction. So extinctions happen not just because of planetary things, but also um, from human extinction. Here is a picture of Martha, who was the last passenger pigeon, who died on September the 1st, 1914. So I guess I missed my chance to light a candle a few days ago for Martha. She died in the Cincinnati Zoological Zoo. The passenger pigeon was determined because of they were very easy to catch and eat. Certainly there have been a lot of extinctions on our planet caused by humans because we found them delicious. Understanding geological time and Earth history. Earth's history can be understood through geologic time. We determine these through certain events. We divide them into ages. So we call it the age of glacial advance, a volcano erupting, an ocean base forming, a mountain belt forming. Age determination aids in our understanding of the rates of geological processes and the interactions. We have relative time tools, so being able to tell that one strata or event is older or younger in comparison. We do this by relative dating, and so early scientists made observations and developed relative time dating tools. This is our last thing we're talking about. So Nicholas Steno or Niels Stenson had the idea of the law of superposition, which means it seems so obvious, but if something's underneath something, it's older, right? So if you have different layers of Earth as you look through time, a lower strata will be older. William Stratus Smith talked about fossil succession. Fossil succession means as you go down through the strata, if it's found in a lower strata, it's also older. So Niels said top strata is younger, lower strata is older, and William said, well, if it's found in that strata, then it must be old. Nobody just dug and planted it there, which was blasphemous at the time because people thought that God had put it there. And still to this day, there are parts of our planet that there are populations who do not believe it. There are combinations of relative and eventually absolute timescales, and we came up with geologic timescales. So here is a nice little map of, first we have the largest blocks of time are eons. Eras, we have the Paleozoic, Mesozoic, and Cenozoic, which are then divided into periods. So the very popular book and then movie series Jurassic Park would have been the mid-Mesozoic. And then here are the boundary dates in between. The periods are then divided into epochs. We quite often talk about the Holocene and the Pleistocene because that's where humans developed from our earliest ancestors. Here we have the geologic timescale. I'm introducing this. I'll let you go into further in your homeworks. Ask questions about this. In summary, we're just about finished. The Earth's position in the solar system is perfect for evolution of the three physical systems, permits a wide range of life forms, and this has to do not just with the atmosphere that we have carbon dioxide and now oxygen, but water. We are at the right distance from the sun to have water in liquid, solid, and gas form. The physical systems are the geosphere, the hydrosphere, and the atmosphere. We do not consider the biosphere, which is the fourth, a physical system because a lot of that system moves around on its own. It's not developed. We're not dependent on a lot of physical processes. The physical systems interact to provide niches for the biosphere, including humans. The geosphere is differentiated into the core, mantle, and two types of crust, continental and oceanic. And the state of matter of a differentiated Earth, we can detect seismic waves, solid cores, etc. And I'm going to, the last part I had to increase the speed, so I kind of went quite quickly. But were there any questions for me on this? Or on the homeworks from last week or this week? We'll go ahead and talk about that. I think we're all kind of, let me stop this. I'll finish recording.